Okay, so welcome back. And we were actually discussing in the last lecture on this particular application of image blending and how beautifully we can use the concept of image pyramids to come up with a reasonably good image blending, right? And I also introduce you to another way of blending, Poisson blending, which also you can try yourself and see the improvements. Okay, so let's move on to the next application, which is actually image compression. Okay, so let's see that. Okay, so why and how, that's very important, right? Any particular application that you come up with, you should ask these two questions. So why image compression is required? Okay, so it's quite obvious. I think those who are in this modern day world will not say that it's not needed, right? Because we are talking about a lot of digital data and we need to store that and we need to transmit that. And if you don't use any compression, direct storage and transmission is almost impossible, right? I mean, it will just consume your bandwidth, and whatever amount of bandwidth that you have, whether it's 100 mbps or whatever it is, it may not be really worth it then. Okay, so it's important that we compress the image, because it's extremely useful for storage, because you don't occupy the entire hard disk space that you have, and it's easy for transmission. Okay, let's take an example. Okay, so uh, let's take a 1024 cross 1024 RGB image. Okay, so it's not really a high resolution image by modern day standards. It's really low res. Okay, and let's assume that we are going to use 8-bit quantization. Okay, so 256 levels. Okay, so let's assume that. Okay, so if you see what space this single image occurs, I mean takes up. Okay, so it will be 1024 into 1024 into 8 bits into 3 channels, right? So that is a total number of bits, and you divide by basically kilobytes, then you get something like roughly 3 MB of space. So if you don't do any image compression, an image which is not really high res image with really moderate resolution will take up almost 3 MB of space. And imagine a video which has 30 frames and maybe 1 minute duration. Oh, that's really going to be enormous, right? So definitely the path forward is like you compress the image. Okay, and now how compression is possible? Now next question is that, obviously, right? So moment we decide that we need to compress the image, now the next thought process comes is how to compress the image, right? So this figure actually shows here 3 sets of images. Okay, let me just use the pen here. Okay, so 3 sets of images, we'll treat them individually. So let's consider this image, for example. So if I consider this image, by now you should be able to tell me, even without plotting the histogram, that it has finite set of levels, intensity levels, right? So approximately I think around 5 levels you can say. Okay, 1 2 3 and maybe 4, I think. Yeah, that's it, and background included. So it's sort of, I think, 4 levels, right? So 1 here. Okay, so this is 1, the white is second, this is 3, and then this you have 4. I think that's it, pretty much sort of covered. So you have 4 levels here, so that means only 4 intensity values are there, and really representing all the intensity, all the basically intensity levels with 8 bits is really useless in this case, right? It's really only 4 levels, so you can, as good as you can represent maybe 2 bits in this case. So you really need to think about compression. Okay, so that's what this picture actually shows you. Now if you consider this one, okay, this one is interesting, because if I take if I consider this line alone, I mean this direction alone. Okay, so if I take, let's say, one particular intensity, that is just repeated throughout. Okay, so shall I actually basically all these pixels, do I need to really represent, because I know the structure of the image, it has something. Okay, and it's possible to compress, because I know that entire along this particular, any line that you take, any horizontal line that you take in this image, it can be represented by the same intensity, right? So that means I can save a lot. I don't need to actually represent all pixels, right, by 8 bits in this case also. So there is a possibility of image compression. So this is the interesting aspect about it. So this is a pattern, you can always see that. So if you go to a transform domain, you may be able to represent or compress this in a lot more efficient way. Okay, now consider this last image. Okay, so this image is interesting because it has only one value. Okay, so it just has one value, and it may be some value, maybe 128 for example. Okay, so it just means it can be represented by just one bit, because it doesn't matter if it is represented by 128 or it represented by 0 intensity or it represented by 255, because for us it is uniform image, nothing is there throughout, it's just one value. Okay, so this is the beauty about it. So if I take Fourier transform of this or DCT of this, I will have only one value which is at u equal to v equal to 0, remaining everything will be 0. So that means I can just discard other coefficients, I don't really need. Okay, so that's exactly what makes it possible. Okay, image compression is needed, we know that, and it is possible, now we know it, right? I mean, so basically this is the basics of what image compression is all about. Now moving forward, I just want to introduce to you some image compression standards. So it's an evolving field, you will come up with lots and lots of standards. So some of them you are already familiar with. So if you have a still image and if it's binary type, you have these sort of compressions. Generally we talk about the continuous tone images, right? Multi-level images. So JPEG is the most popular one, I would say, in digital cameras. Most of the digital cameras use JPEG, and we will be discussing in detail about JPEG as a prototype. Okay, so moment you understand JPEG, you should be able to understand any other standard, because it's sort of it's called as a prototype method for image compression. Okay, the basic behind JPEG, interestingly, is the DCT, discrete cosine transform. Okay, then how JPEG LS, which is sort of modified version of JPEG, where you use adaptive coding and all. So we'll not go into details of these other standards, but we will go in detail of JPEG. Okay, JPEG 2000 is wavelet, so that I'm just thinking about assignment 2, where you need to do JPEG 2000, where I will give you the code for JPEG. You may have to expand it to JPEG 2000. Okay, so and then compare the compression between JPEG and JPEG 2000 for yourself. Okay, then you have BMP and so many standards. So I have maybe anyway definitions coming up, so I won't go into details. And on the video, of course, MPEG 1, 2, 3, 4. MPEG 4 is definitely most popular one, MP4. Okay, so that's the versatility of the standards, and in fact MPEG is based on JPEG. Okay, so let me just show you some of those standards. So you should be knowing JPEG, quite popular. Okay, so we'll take it in more details, and you can see it's DCT, and JPEG LS is, as I said, adaptive prediction. And then JPEG 2000, as I said, it's based on discrete wavelet transforms. Okay, so all these you studied, right? I mean, adaptive coding, of course, you not studied. We'll introduce one of the interesting way to code the image, code the data. Those who have studied information theory and statistics are well aware of the coding techniques. If you're not, don't worry. We'll just introduce the one particular coding known as Huffman coding, and then we will discuss in detail about that. Okay. And then video standards, some of them. Before that, BMP is Microsoft, so it's Windows basic standard. PDF is ever popular. TIFF is also very popular. PNG is also very popular. So you can see the descriptions actually. Okay, this is taken from the textbook, so you have more details in there. And video standards, you are actually studied many of them, right? I mean, it's quite interesting in that sense. Yeah. So. So basically what I meant is some of these video standards, for example, JPEG is quite popular to you, right? And QuickTime, if you are using Apple computers, you are quite popular with QuickTime, and WMV if you are using Windows, right? So all these are formed by different companies, different entities, and they are standardized, so that those who are using it should be knowing how to compress and decompress the image, right? So because moment you compress the image, you store it, you transmit it, but at the receiver side, or when you open that image, you need to decompress it and show it in the original resolution as close as possible. So some of these standards, in fact most of these standards are lossy, some of them are lossless. So there are various options that you have, and since our topic is restricted to JPEG, I may not be explaining all the concepts, but those who are interested, it's actually quite easy to follow moment you understand JPEG. Okay, so let's actually go into the generic architecture of image compression. Okay, so this is how a generic architecture looks like. Okay, so you have the image or video, so a T stands for video, so just consider image, there's nothing there. The first operation that you do is a mapper. Okay, so mapper is nothing but something like a domain transformation. So in the case of JPEG, we are going to actually replace. So some example for mapper is basically something like DCT. Okay, so you transform the image to a different domain. So map the image to a different domain where the image is more sparse, right? The image is more sparse in the sense like it won't have all the coefficients. Most of the coefficients are really near to zero, and you can safely discard them. So there is a chance for compression. Okay, so that's the first step. Okay, you map the image, and after that what you do is you further reduce the you further increase the sparseness, or you further reduce the intensity. So for that you need to do the quantization operation, which we discussed maybe in the first lecture or second lecture, right? But here it's not that quantization. Here what I'm talking about is in the domain. I won't be retarding all the coefficients. I will just discard some coefficients. So for that I do some sort of quantization. These are interesting. So even there were many papers on proposing new and new quantizers, okay, for example, for some time. Okay, so this process is basically, there are two aspects to it. One is actually to reduce, or to, it's like a thresholding operation, reduce the significance of coefficients, I would say, some more coefficients, okay, significance of coefficients, okay. And this is one way of thinking about it. Second way is actually by quantizing, what essentially you do is you limit the number of options, right? That's an interesting thought, and a different thought to have. When you quantize the intensity, what you are essentially doing is you reduce the level at which the intensity can vary, right? For example, when you have an 8-bit quantizer, you are limiting that your intensity can only take finite set of values, right? 0, 1 up to 255. Right? If you have let's say 16-bit, then you have 2 raised to 16 levels, right? You are having further division, so finer resolution. So then there is an important aspect. So when you have quantization, since you are limiting the number of intensity levels that you can take, you are actually reducing the number of possibilities, and in that way you are increasing the redundancy in the data, because there will be if let's say you go away from 16-bit to 8-bit, so that means the number of similar values are going to increase in 8-bit, right? Because you are reducing the number of options. So most of the values may quantize to 0 or 1 or 2 or 3 depending on the rounding operation. But the number of, or the redundancy, the number of occurrences is going to increase. So that's a very important aspect. So basically you will increase the redundancy, okay? So this is important because the next step is symbol coder, okay? So if you want to code, so basically what you do is you take the image, you map it to a different domain, then you quantize it. Then after that what you do is you serialize whatever the matrix is. You have a matrix till this stage. After that you serialize it, and then you consider a group as a symbol. And then what you do is you, from information theory, you take one of the coding scenario and you further reduce the resolution or the bit size required for the entire image, okay. So for this coding, if you have more redundancy, you have better ability to code, okay. So those who studied information theory and statistics can already know what I'm talking about, but others you don't have to worry, I will show you with example, okay. So basically it's important, the quantizer solves you two purpose. It actually reduces most of the sickness, sort of a thresholding operation, soft thresholding you could say, on the domain coefficients. So most of the coefficients are discarded, and also by doing that you are inherently increasing the redundancy because you are allowing the values to take more in number, okay. So it's easy to visualize. If you go from 16-bit to 8-bit, the number of opportunities are reduced. So if the number of opportunities are reduced, you tend to repeat, right? That means the redundancy is increased, okay. So that's the meaning of it. So moment you have it, you have a compressed image here, right? You have a compressed image, and now this is ready for storage or for transmission. If it is transmission or storage, whatever it is, at the receiver side or at the decompression side, you have to do the exact opposite, okay. So you do symbol decoder. So the moment you know what type of coding I'm using, I can do the opposite of that, and then you do the inverse mapping, okay. So just these two processes are reversed, and this is the lossy part of it. So you can't reverse quantization because we already know that. I had a question about that also. Quantization is a non-linear operation. The moment you do that, you are done. You will never be able to recover the signal. So this is the lossy part of it. So if you avoid quantization, the compression is mostly lossless, and then if you have quantization, you have lossy. You have loss already there, and that cannot be reversed back. But you can reverse back the decoding, the encoding part, the coding part, and you can even inverse map it. So if you have DCT here, then you have IDCT here, okay. So for example, in the case of JPEG, this will be Huffman coding. Okay, so we'll have, I think I have a slide next, and this is inverse Huffman coding, and that's it. So this is all about compression. It's quite easy. I mean, it's not really difficult to follow. I hope you are not lost in this. Okay. So let me just discard all this. And now let's actually talk about JPEG. Okay, so I'm not going to introduce to you all the compressions because that will be terribly boring and it almost takes maybe 2 to 3 lectures on that, right? So we don't need to do that. This is just a subset of our course. But it's important that you understand JPEG so that you are able to follow any other standard. Okay, so JPEG, it stands for Joint Photographic Experts Group. Okay, if you never know it, it is actually a standard. Okay, so which was proposed for compressing the images originally, and there's a small history around it. You can read it. Actually, I don't want to read what is written over here. So there were a lot of algorithms proposed, published in the name of JPEG, but eventually it was not actually proposed as JPEG. Okay, so JPEG is a much simpler standard version which was advocated at the time, and it is the full form for original JPEG. I mean, they are using something known as JFIF, and its full form is JPEG File Interchange Format. Okay, so this entire thing is typically known in the outside world as JPEG or JPG. Okay, so that's it. So it's a very simple algorithm, and we are going to discuss about that. Okay. Okay, so I think that's it. I think it's, you can read it and see for yourself the history, and I would like you to just Google search it and see the entire history, and it's very interesting to read through. Okay. So what is the crux of it? Okay, so I think this is one of the reason where we started lecture 1 or 2 with physics of vision, right? Because this is important, because as I said all the time, who is the judge of the algorithm, the final judge of the algorithm? It is nothing but the human eye, right? The perception, right? So JPEG is actually easily making use of, I mean, the JPEG compression idea is actually designed specifically for human eye. Okay, so it's just making use of the properties, the biological properties of human sight. So 2 aspects. Okay, so we are more sensitive to the luminosity of color rather than the chromatic value of an image. That means we are not really sensitive to the color part of it. We are more sensitive to the intensity, the luminance part of it. Okay, the luminosity of part of it. There is a reason why I am stressing this, because the very first step of a JPEG, if it is a color image, is to convert that into something known as luminance chrominance image, YCR CBR image. I mean YCR BR image. Okay, so we'll discuss on that. So the moment you have a grayscale image, doesn't matter, no problem. The moment you have an RGB image, the color image, you convert that RGB into something known as YCBR CR. Okay, so that process is straightforward matrix multiplication. So what I'm saying actually is this. Okay, is basically this. So you have an RGB image, you do some matrix operation, just some matrix multiplication, as simple as that, you get something known as YCR BR. Okay, sorry. So this part is known as the luminance, and this part is the color component. Okay, so our human eye is very sensitive to this guy and is least sensitive to this guy. So what they do is actually they do a lot of compression on this and very little compression on this. Okay, so that's a generic idea that is leveraged in JPEG. Okay, so we will not discuss in much detail about that, but we will discuss about other aspect, how to compress and all. Okay, so but this should be kept in mind. Okay, and then we are not particularly sensitive to high frequency content images. Okay, so edges, yes, we are sensitive, but sometimes what happens is our human eye, I mean, as brain basically sort of interpolates everything. So sometimes many of the high varying things are really not sensitive. Okay, so even if you discard that, you won't be really perceiving that in the image. Okay, that's an interesting aspect. Okay, so there are many literatures which are exclusively discussing these 2 aspects, and those who really want to know more about it, please go ahead and see into that. And the whole point of discussion is like JPEG is leveraging those concepts. Okay, now let's go into the details of JPEG compression. So this is what it looks like. Okay, so this is what I was telling. So you have the RGB image, the typical color image, you convert that into YCR CB. Okay, and then you are more concentrated on this part and less compression on this. Okay, so you do it independently, that's what I'm saying. So for our discussion, let's ignore all these RGB, YCR, CB, etc. We treat it as a grayscale image and then discuss about the remaining aspects, which is the critical, okay, the image processing aspect of it. Okay, so the conversion from RGB to YCRCB is just a simple matrix multiplication. I just want to show you that. Just give me a moment. I have a Wikipedia page. So this is what exactly this. I'll just scroll down to the relevant part. So this is the JPEG part of it. So YCBCR is obtained by a simple matrix multiplication, something like this, where R, G, and B are the 3 channels in the color. So it's just a matrix multiplication. That's all. Okay. So coming back to the slide. Okay, so we have this. This I just want. I think I already explained it in the generic form, but let's concentrate in a very specific form here. So this part should be very clear to you now. Let's concentrate from here. Okay. So now what we are going to do is treat the image in terms of some 8x8 blocks. Okay. So this we discussed briefly in the hands-on session on the transform, right? Where I said that instead of taking the image transform for the whole image, what people typically do is divide the image into small blocks, non-overlapping small blocks, okay, and then take the transform on that. And that's exactly what people are doing in JPEG also. So they take a 8x8 block all through the image, non-overlapping, okay. So you divide your image into 8x8 blocks. Each block you take the DCT, okay. And the reason why DCT, as we had discussed a lot for, it's better than Fourier transform, because it has a better compact representation, and it has that artifact issue is not there at all, and that results in better compact representation of the image, as well as sort of increased resolution compared to DFT, right? And one more major thing is, like all other transforms that we discuss is tuned to a particular application, like slant or Hadamard or wavelet. You really it's not a very generic transform. So they all started with DCT because it's a very generic transform. Okay, so 8x8 block, each 8x8 block I take the DCT, okay, so discrete cosine transform, and then what I do is, in the discrete cosine transform, each of those 8x8 block, what I do is quantization. Okay, so basically I divide those coefficients, cosine transform coefficients, okay, by a certain matrix, and I will reduce the value. So some I think we discussed this briefly, and I have anyway in the next slide also. If you see the discrete Fourier transform definition or examples, what you might have observed is, like, let's say this is the final discrete cosine transform matrix that you get. Okay, so you have the values, right? Okay, so you have all the values. This guy is of course u equal to 0, v equal to 0, and this is the highest frequency, right? Okay, so highest frequency in terms of u equal to whatever number, n minus 1, v equal to n minus 1, whatever, if it's endpoint DCT. Okay, so what essentially you observed, or we typically observe, is that this part will be heavily occupied, and as we go towards here, it will be really very less value. So what you do essentially by this quantization is, this entire thing will be divided by another matrix of the same size. Okay, so in this case, anyway, this will be 8x8, right, for us. Okay, so this will be divided by another 8x8 values, and what essentially you further reduce these values. Okay, so whatever this part, you further reduce it, and this is not really touched much. Okay, so such a quantization you will do. Okay, and then rest of the part is basically then is, I mean, these two part we will specifically discuss, so I don't want to discuss much in this slide. So then we do some sort of, instead of a raster scan, instead of something like a scanning the coefficients like this, what we do is we do this sort of a zigzag scan. There is a reason. Can somebody explain me? Can somebody think what is the reason why we are doing this way? It's very simple, right? Because if we go this way, what we are doing is we are definitely growing in a gradual increase in frequency, but after this there is a sudden jump, right, to a low frequency. So, but interestingly, as I said, this set may be having high values, and others are just can be discarded. So that means if I go in a zigzag fashion, I will have all the high values closer. So if I go this way, then this, then this, then it means the values sort of has a decreasing trend. Okay, so that's very important. And also another thing is, like, this frequency and this frequency are closely related, right? And this frequency and this frequency are closely related. So that's the reason why they choose this zigzag pattern instead of going like the raster scan pattern, right? So it's not used. Okay, so you do the quantization, then basically you do this sort of zigzag arrangement, and then after this you will have a vector, right? This is a matrix, and after that you have something like 1 by 64 in this case. Okay, so 1 by 64 till this is 8 by 8. Okay, so if I take this sort of a zigzag arrangement, I will get a 1 by 64. So each of the region in the image I get a 1 by 60. Each 8 by 8 region in the image I have a 1 by 64 vector representation. Okay, and then after that you do some particular operation to reduce the redundancy. Okay, so as I said, quantization will induce a lot of redundancy, lot of values will be repeating, and you purposefully did that, you enable that, and now after that I can do coding. Okay, I can reduce the redundancy in the data, and then I can transmit it off. Okay, so this is the final data that you have when you have a .jpg or .jpeg file. This is the final representation that you have. Okay, so we will go in details of each and everything. Okay, so don't worry, we have all the details in the coming lectures. So if you don't understand this step, don't worry, we are going to take each of these steps in detail and understand thoroughly what's happening. Okay, so just to conclude this lecture, so this guy over here, okay, so this guy over here is the .jpeg format that you have. Okay, and in this lecture series we only consider grayscale images for simplicity. Okay, so even if I have a color image, I ignore these two steps, but you always remember the original JPEG algorithm has these two steps. Okay, so it is, you can treat something like you are doing it individually on YCR CB component. Okay, individually. Okay, so with that I will stop this lecture. Oh, I made a mistake in the previous slide, right? It is CRCB. I think I put CRBR or something like that. Okay, so Y red chrominance, blue chrominance. That's what it means. Okay, Y is luminosity. This is chrominance in red, and this is chrominance in. So this is the color part. This is the brightness part. Okay, so that's it. Okay, so we will stop the lecture here, and now next lecture we will explain in detail each of these blocks. Okay, so see you in the next lecture. Thank you.